Hello, everyone. Welcome back to the Chilean Probability Seminar. It's for me a real pleasure to introduce you to Lauri Viitasaari from Aalto University. He's going to talk us about data-driven forecasting based on fractional Brownian motion-driven SDEs. Lauri, the floor is yours.
Thank you. So first of all, I would like to thank for the invitation. It's my pleasure to give a talk. And I don't know, it's probability seminar. I put Santiago. I don't know whether I should have put Chile or maybe Inkeroinen because I'm located in a small village in Finland now. But yes, although it says that I'm a businessman, but my background is in math and probability theory. So I will give you some Finnish honesty. So I don't really care about the financial time series, but I have to put these things because I'm at the business school. So we focus on probability, don't worry. And let's go. So basically, joint work with my student Mahdi Deshiri and then with Kerlins Martinez, who is also in the audience, I think. And basically the motivation for the work started when we started to discuss with Kerlins about estimation of coefficient functions in fBm-driven SDEs. And then we found that there's not actually much. So then we started to look at what we can do. And yes, so I heard that it's like 1 hour. I try to spend it all, but here's the outline. So let's see how chaotic it will be. But I will give you an introduction, kind of the motivation for the problem, some background, and then I will describe the main result and show kind of some particular cases where you can actually have something concrete. And few simulations. Nowadays, it seems that you always have to convince your audience that you actually have something that works. So we have that. And then maybe an interesting part to you would be also the sketch of the proof. So I will explain the main ideas, kind of where everything is based on. Okay, so let's start with the financial jargon. So what you typically have, okay, let's think that you would have a time series, maybe many time series describing whatever things, financial things or something else. Typically, you have these complicated dependencies, not only in the time, right, but also on the spatial dimension. So the time series might depend on each other. So you should kind of think about these as multidimensional problems. You observe vectors of time series and multidimensional versions, but then on top of that, you might have a long memory. So basically that the current state depends from the history or from a long time ago, rather than having only kind of short dependence. And basically for this kind of, if you kind of look at these practical applications, you might want to incorporate many different things. So you might have these complicated trends, typically nonlinear, let's say seasonalities, for example. Then it might be also that what we have observed empirically is that in many cases you kind of don't have, let's say, stationarity of the time series, but you rather might also, the variance might be changing. So the fluctuations of the series changes in time maybe, and also kind of depending on where you are. Let's say, for example, in the typical stock price behavior or stock index behavior is that when the price go high enough, then you get higher volatility. So the volatility is changing because when the price goes up, then people starts to trade more and you kind of get these fluctuations there. And then you would also need this memory effect. So maybe you have to look at really into the past, not only kind of short time, like 1 week, but rather 1 year or something like that to the past. And on top of that, you need this also the spatial dependencies. So your time series depend on each others. Let's say the oil price maybe depends on the interest rates or whatever. whatever you are modeling. Okay, and let's look at some kind of baseline typical approaches. So in many basic courses, maybe many of you know the ARMA modeling, which is the traditional one. So works nicely if you have stationary series. So typically you do something first that you get a stationary series, and then you try to use ARMA model, which is a linear model. So you only can capture linear dependencies, but then also the problem is that it always automatically has kind of short memory or relatively short memory. And what this short memory means, it basically means that the correlations in this case decay rapidly enough to zero. Okay, so if we go beyond stationary case or ARMA models, you can use some decomposition methods. I think one of the modern ones is Facebook Prophet. And this is also kind of used a lot. So you kind of try to decompose your series into various components, trend, seasonal component, and then what remains is then something which is maybe stationary random shock. So you kind of think that you have deterministic parts there, and then the fluctuations around the deterministic part are coming from some random, typically stationary shocks. Okay, then nowadays we have neural networks everywhere. So there you can kind of capture nonlinear dependencies. You introduce the activation functions, and these can also capture memory effects. So like the LSTM networks are quite used nowadays. But then of course the downside, or I'm not sure whether it's a downside, kind of it is. They're very data hungry because kind of once you have a lot of number of parameters increase, then of course you need more data to have good fit. Otherwise you will start to do overfitting. And then it's poor generalization or poor forecast. And then another way is to use SDE models, which is kind of thinking of continuous time series. And this is where we focus on today. So we kind of think that the time series comes as a realization of, or as a path of some solution of stochastic differential equation. So this is what we have. So we kind of think that your series or your observation, it's a function. Think of it as time series or random function. It's a realized solution to this kind of stochastic differential equation. So what we have two things. We have the drift term that might depend on the time point you are, and then also on the solution. And then we have the noise term. And with the noise term, so we kind of have the random noise there. Let's use it as general now. But then the size of the randomness is, or the kind of the fluctuations in the size of the randomness, these random shocks, are incorporated to the diffusion function. So again, you can think of this like the volatility in financial context. It might depend on the time you are, but then also kind of on the level where you are. If you would, for example, consider X to be a stock index. So then kind of it depends where you are, and relating to this example I mentioned. And okay, even though it's written like this, think of it all the time as kind of multidimensional version. So if you think about multidimensional, then X would be a vector, and then also F and sigma would be kind of, or the noise would be also vector, and sigma could be, for example, a matrix. So then you kind of write the thing component-wise, and kind of what this is just a short notation. So, but keep in mind that kind of you might also have multidimensional version, and then also the dependencies between these different components are incorporated to these functions F and sigma that depend now on all of the components. And what's the idea here? So kind of we think of this time series in continuous time, and once you have the drift, you can basically incorporate these trends, seasonal effects, whatever. the deterministic part in a sense, even though it's not fully deterministic, but you can kind of think of that as some sort of trend you are following, and then the latter part is the random shocks around this. And as I mentioned already, so here you can kind of also incorporate these changes in the variance or in the size of these random shocks, let's put it that way. And then whenever you consider the noise to be more general, you can incorporate memory effects there. So in the title, it said fBm driven, so that's the prototypical example, but a priori, we don't need that. And what is kind of nice with this is this model can capture, I would say, essentially arbitrary dependency structures. So if you choose F and sigma suitably, the solution X can have basically almost any distribution you want and any kind of dependent structures. And there is actually previous papers, even by me, if you kind of drop the drift part, you can still kind of construct arbitrary distributions as a solutions to SDEs. So this is kind of the pep talk or the motivation that kind of, if you think about this, it's not a restriction. You can kind of think that, okay, whatever your data is, you can find the correct functions that give you precisely these distributional and dependency properties, or almost at least. But from the modeling perspective, we are happy with almost. Okay, some particular examples maybe to relate to something more familiar. So if we would think about the Brownian motion case noise, and if we take a very simple drift and constant diffusion, you just get the classical Orstein-Uhlenbeck process. And linking to this ARMA process I mentioned, this is just a continuous time analog of the autoregressive process of order 1. Okay, let's generalize this. So the next one, if you change the noise, let's call this a generalized Orstein-Uhlenbeck process. So if you change the noise from the Brownian motion to something that has stationary increments, this covers all continuous time stationary processes. So this is also a non-result. So even in a multidimensional case, so if you have a stationary vector, you can always characterize it as a solution to this with certain noise. And then the relating to financial things, so the Black-Scholes stock price model is again certain linear drift, linear diffusion, and with the Brownian motion, this gives kind of the Nobel Prize winning old classical Black-Scholes model. And in the same way, you could kind of generalize that by simply changing the noise to something else. But these are, of course, parametric models. So you cannot really get anything out of these. Like in the Black-Scholes model, you have log normal distribution. In the Orstein-Uhlenbeck case, you have Gaussian distribution and so on. But if you change your drift and diffusion to something more general, you can kind of fit that to your data. And what's our target? Okay, now I have motivated you that you kind of can get anything. So this SDE should fit to the model, or sorry, fit to the data you have. Okay, so then the target would be that you need to find these coefficient functions, right? So you want to find, given the data, you want to find the drift, F, and then the diffusion coefficient sigma. And we try to do this in a non-parametric way. And basically, the Brownian motion case is somewhat studied already. And what we want to do is that we take something more general, and in particular, the fractional Brownian motion with Hurst index h above 1/2. But a priori, this is not needed. So anything Hölder continuous of order over 1/2 would go. But kind of let's think about the fractional Brownian motion. And if you're not familiar with the fractional Brownian motion, it doesn't matter. just you need to know that it's kind of something else as a noise, and then you can solve the equation. And now our target is to find, observing the path, finding the coefficient functions f and sigma. Okay, and this is kind of somehow the target. But from the theoretical perspective, what we have tried to do, or what we have done, is that thinking that, okay, we find the estimates, whatever method we have, we find from the observations the f and sigma, or our approximations for those. We want to quantify the error you make, basically. So what's the error you make if you would replace your path, so your solution, with the wrong coefficient functions? So same noise, but a bit wrong coefficient functions. And we want to quantify this error, and this kind of in terms of the error you make in these functions, and this would then kind of allow you to know that in what norm or in what way you should approximate these functions. Okay, and let's look at the results then. So let's fix the notation first. So basically what we do, we look at some compact interval, can be arbitrarily large, but you kind of fix your time interval of observations. And on that interval, we look at the fractional Sobolev space equipped with this norm. So you kind of have two parts here. One measures the location of the function. So if you think about it, we try to fit to data. So we observe a path, you try to fit there, so you should follow the location. But at the same time, we want to also follow the fluctuations. You see the random fluctuations. And for that, we have this semi-norm part. So alpha is a parameter here. And basically, if your function is Hölder continuous, this is somehow measures the fluctuations in the Hölder norm or close to it, but in the fractional way, fractional Sobolev way. Okay, and why we use this norm? So actually the motivation stems from the fact that once you have your SDE, this is the correct space you should look at where your solution lives. So this equation here, under nice conditions on f and sigma, of course, basically has a unique solution precisely in this space. Okay, and this kind of suggests that this should be maybe the correct norm where to measure the error, and also it does both required things at the same time. It measures the location and also follows the fluctuations, because this semi-norm part looks at those. And this is kind of what we do. This norm we use for the solution itself. But then what we wanted to do, we want to quantify kind of the norm where you should approximate your functions. And in particular, we want something that is independent of the solutions in a way. So you want to have your coefficient function or your target function, let's say f or sigma here. And we want to approximate in these kind of LP type norms. So what you have the LQ norm in space, and then the resulting thing is basically the raw LP, L raw space in time. So kind of this is the product space of two LP spaces. And what is kind of worth to note is that this does not look at the solution a priori. Only way it looks at it actually that here I intentionally did not write the domain of the integration in the space variable. And that will be eventually a large enough compact set carrying the solution. So kind of idea is that, let's say your path is continuous. your solution is continuous. It goes somewhere, fluctuates in the d-dimensional space, let's say. You just take large enough ball to contain the trajectory. And that you can use as an integration domain here. And this is now the kind of the, let's say, part of our main results. The main result is more complicated, but I always try to hide the boring technical details in my talks, and also I skipped part of it. I will give some remarks soon, but this kind of, in this setup, what I have explained is precisely now what we have. So what we do, you have your true solution, that's the x. Then we have our approximated one or the estimated one with the wrong coefficients, with the approximated coefficients. And then we look at okay, what's the error you make in these approximations of the coefficient functions? The difference in the solutions in this alpha infinity, in this fractional Sobolev norm, can be bounded. This means that up to unimportant constant, so you multiply with some constant there, depending on a lot of things, but unimportant constant, with these kind of 7 terms. But what you see is that you precisely see this kind of LP or the norm of the product of LP spaces for the actual difference of the functions, so this part and this part, and then also the derivatives. So you have time derivatives for both differences, then you have the spatial derivatives for both, so the gradient, and then for the sigma, for the diffusion coefficient, you have also the cross derivative. So kind of the second derivative, but one in time and one in space. And this is kind of this error what we have. So basically suggesting that if you try to estimate these functions from the data, you should try to find something so that these quantities converge to 0. Then you get close to your solution. Okay, so remarks. So basically, first of all, what we want to emphasize is that there are some results, previous results, in a special cases in the fBm-driven SDEs, that if you have L infinity convergence of the coefficient functions, then you get something. And this would mean kind of that you have pointwise convergence. But what our result says is that actually less is enough. So LP is much weaker, of course, than pointwise convergence. And this allows to do estimation in, well, let's say, more rich class of possible methods for the estimation, because you need weaker convergence. And then, okay, also this error can be kind of, if you look at that, you have all these terms. So we could actually make even one more upper bound. And what you would get is simply certain order Sobolev norms here for the error in drift and for the error in diffusion. So that would kind of, if you make that upper bound, it would simply say that the certain kind of Sobolev norms are enough for you. And in particular, you don't need the P to be infinity, so something less is enough. And okay, then of course the warning is here that in this general setting, what I want to emphasize is that if you think about now in practice your setup, let's say you observe one trajectory, you cannot find these coefficient functions in general. Why? Because if they depend on time, then you have kind of only one time slice of the function of the functions. Let me go back to this. So you see my cursor, I think. So if you have kind of the time dependence here as well, you kind of only have one single value and you cannot say anything. But if you drop the time dependence, then maybe when you run the X, you kind of see everywhere the F, and then you can do something. But yeah, and then this was what I said, it's kind of only part of the result, of the main result. So what we actually did is that we separated the error you make by thinking that what you have is that you also need to estimate the Hölder index, or in the fBm case, the Hurst index, which are the same. So that kind of controls the memory. And what we are kind of thinking that you only observe your realization, your data, and you don't even know what is the Hölder index in the underlying noise. And you don't know the coefficient functions. And on top of that, you also kind of need to discretize in time. And this gives rise to three different errors. So kind of one from the time discretization, but this is well studied, so nothing new there. Then one from this approximation error, and that was this theorem, the part of the main theorem, what we have. And then one coming from the estimation of this Hölder index. And that's also our new contribution. And for that, now I kind of, with a tiny abuse of notation, but kind of comparing two solutions. One is the true one with the correct Hurst index, and one is with the estimated one. And again, if you look at now in this correct fractional Sobolev norm, what's the error you make? It's up to constant proportional to the square root of the error you make in the estimation of H. And kind of these are the two main contributions we have. And let's look at these particular cases. I still have like 25 minutes. Perfect. So these are kind of what I showed you are our general result, but then to get something concrete. So for example, in one-dimensional case, you can find from the literature this kind of estimator from a single realization of the solution for this Hurst index H. And if you use this one, you actually can bound this thing here. You know how close it is, and you can actually really get a concrete convergence rate for the error you make in the solutions. Here it's up to constant proportional to 1 divided by m to power, let's say, h divided by 4, up to log term and maybe minus epsilon, because gamma cannot be up to h. But you kind of get explicitly the rate there. Okay, then for the other case, this was actually kind of the whole motivation what we had for the project was that we wanted to approximate these coefficient functions with neural networks. And we basically found nothing. And now kind of coming back to this motivation. So again, kind of just a concrete example. So if you would estimate these coefficient functions, the drift and the diffusion, with certain kind of neural networks from this class, don't worry about what the class is, but certain kind of neural networks, you can actually find an explicit bound for the rate. So n is kind of the amount of, you have the, okay, here you have the coefficients, you have the activation functions, and then you take a sum of combination of those, and how many you have gives you kind of the bound here. But again, the main message is that you can kind of find explicit error that you have if you use this kind of approximation. Okay, then to convince you that this actually works, so basically, what about in practice? Before going to the images, nice looking images. What we did so far, we just studied the theoretical things, so kind of giving guidelines, let's say, to what norms to use and what is the size of error you make. Basically, in practice, I would distinguish two different setups. So even though the title says time series, there, as I mentioned already in this warning, you want to drop the time dependence on these coefficient functions. But in that case, let's say you observe long enough series, then there are methods how you can actually estimate the f and sigma, and you can kind of study the error you make in these LP norms to get something concrete for the error you make in the solutions. Okay, and then another one where you would have the time dependence, which is also typical in machine learning setting, is the functional data setting. And there, instead of one single trajectory, you observe a lot of them. So your data is kind of, you get many observations, and each observation is one path. So many realizations. And then you can then, for example, use neural networks by using your whole data and kind of try to find the underlying model that produces this data set, these trajectories. And the latter one is basically what we did for the simulations. Target is basically on machine learning side. So we kind of took the same approach that is typical there. And this is the setting we have. So looking at the fractional Brownian motion, three different Hurst indices. So first one, 1/2 corresponding to standard Brownian motion, kind of giving the classical stuff. Then 0.7 and 0.9, and the 0.9 is kind of almost already smooth. So it's kind of starts to look more deterministic. And then we kind of look at three different models. So two one-dimensional. One is kind of Ornstein-Uhlenbeck type model, constant diffusion, and then linear drift. Then we look at one nonlinear, so nonlinear in both the drift and the diffusion, and then one bivariate case, so kind of to prove the concept in higher dimensions, but only for the middle value of the Hurst index. And then basically we have a network tries to find this neural network that tries to find the coefficient functions. And what we have is basically many trajectories, 500, and then we simulate 500 new paths from this approximated model, and then we update the parameters describing this approximated model. And quite okay performance with 500 trajectories only. No. Not to the end yet. So this is now nice colors, by the way. So the drift results for this Ornstein-Uhlenbeck model. So there the drift is 1 minus x, and the left-hand side is the true one, and the right-hand side is the approximated one. So super good already, kind of very good approximation for the drift. With the diffusion, not so well, okay-ish, I would say. We have a constant diffusion, and now it's maybe we would need more paths. One could try, but still somehow okay-ish, I would say. And the diffusion now kind of measures the fluctuations. So at least the drift we were able to follow very well. And maybe I should remark that in the literature, it's typically the drift is harder to estimate in many cases. Because the diffusion you can estimate with other methods. You don't need neural networks really for that. Then for the nonlinear model, so again, right-hand side is ours, left-hand side is the true one. So again, looks very nice. And now the diffusion is also looks much better. And maybe worth to note is that it starts to look a bit better if you increase the age. Sorry, I forgot to mention. So down, when you go down, you kind of increase the age. So always the left is the true one, right is the estimated one, and lower you go, the larger the age. And this is maybe not surprising because kind of you get closer to the, when age increases, the paths are more regular and kind of less fluctuating, and then it's maybe easier to then it starts to look more like the drift term and you kind of get better results. And then final was this bivariate, so two-dimensional case, works quite nicely. So what, I have 15 minutes. Okay, that's perfect. So what we had is the diffusion was the constant. So basically the drift drives the system, and then you just have random fluctuations around the drift. And the drift is basically going in circles towards the middle. So this red one here is the real drift, and the learned one is this blue one here. The error one makes is here, so pretty low values. So the drift is again very well estimated. And then for the diffusion, it's kind of what happens is that it's constant. And what we get better result when it goes closer to the center. And what the model actually does, it really, you see only the drift in the beginning, but once it gets to the center, then you start to see the noise. And it's kind of visible here in the results. When you get closer to the center, you start to see also the diffusion. You can kind of see it from the paths here. So the red one is the true one. It goes in circles here. You start somewhere and then it starts to go circles to the end relatively smoothly. You don't even see the fluctuations here, but you start to see the noise in the center. And this is precisely what we kind of observed in the previous figure as well. But still, if you compare the blue one and the red one, it kind of okay results, I would say. The learned one is the blue one. And here you see the dimensions, how they go with different paths. 15 minutes to go. So I hope you are convinced. Then we go to the math part. So what we had, so sketch of the proofs, we have two main theoretical contributions. One is in the estimation or the error you make if you estimate the age. And then another one is this coefficient approximation error. So let's start with the simple one, which is the error in the estimation of age. And what? The proofs are like 10 pages in total, so I'm skipping some details, but maybe the main ideas. And what is kind of the main idea here is that if you compare the solutions with two different noises, you can bound this fractional Sobolev norm we need to study. This is what we want to study, this quantity. Up to a constant, it's actually up to constant proportional to the error you make in the noise, but measured in different norm. I would say this is kind of the dual norm in a sense to this alpha infinity norm. And this, on the other hand, you can bound with the Hölder norm. And what you need to do then basically is to control the Hölder norm. And okay. And then what we do is that we show this Hölder norm gives you precisely this upper bound that was claimed in the theorem. And for this, what you actually need to do is basically do the Gaussianity. And maybe I should remark that you don't actually need Gaussianity. You need hypercontractivity of the distribution. But in particular, Gaussian processes are a prototypical example of these. And once you have that, you can actually show that only thing you need to study to obtain bounds for the Hölder norm is to just look at the increments squared and the expectation of that, or the variance of the increment. And for that, what you need is then basically the increment in the variance of the increment should be proportional to the increment in time to power something. And that exponent should be large enough. And in our case, what we need to get to the Hölder norm, you need the time difference to power something that is large enough, and then multiplied with this difference in the what you make in the estimation. And this you have now doesn't have power, but you have variance, so second power here, and this leads to the square root there. And basically what you do is just to have this thing, and then it's just computations. So a nice exercise for students, but takes some time and lots of computations, but you can basically do it. And then another part was this error in the estimation of functions. So here we had this fractional Sobolev norm. And what is basically, we had these two parts. First part measures the location, and the second part measures the fluctuations. And basically, what you can do for the first part, it's to use the pinning argument. And the pinning argument is simply that you remove and add something, use the triangle inequality. So you take ft minus f at some given point that you can choose. And then you are again in the difference. And then fractional embeddings give you that basically everything, the second part controls everything. Okay, I'm skipping some details here, but basically what you need to control the second part. And then comes the trick from the analysis, which is the fractional maximal function inequality. That somehow almost gives you Hölder continuity for functions. Not exactly. It actually holds only for Lebesgue almost all points and so on. But what you can do is that you can kind of, instead of looking at Lipschitz continuity, what you do typically, where S would be now 1, you take the difference in the argument to power something less than 1, and then you look at the reach potential of the gradient. Kind of, you compensate this S that you chose here by looking at the reach potential. And maybe I should mark it here that this actually trick allows also to study SDEs with discontinuous coefficient. This is, for example, what Soledad Torres have done, or we did together. But basically, this is a simpler case where you have the gradient, but one could have even measures here. Kind of, I want to market the trick because it's quite nice in the SD context. But okay, once that is established, then you have the reach potential, and then it basically just potential theory after that. And now you can use the simple Hölder inequality basically to bound the reach potential. You could do nicer tricks as well, but for us, this was enough. And yes, so here you basically, what you get is then some larger norm of the gradient. And you kind of get the difference in the arguments. So this would give you just the difference in the solution multiplied with the difference in the norm of the difference, gradient of the difference. And you use the same thing for both the diffusion and drift part. And basically what you get this leads to, for example, for this difference you make in the diffusion, you get something like this. And these terms are precisely what we had in the theorem. I'm kind of running out of time, so summary is here. Take-home messages. What I want to market again is that this is very flexible model class, the SDE models. And what we have done here is that we have quantified the error that one makes if you estimate, well, the coefficient functions. And what we used this weak type LP norms in the error, which kind of gives nicer or more easily implementable ways to do estimation than pointwise things. And then in practice, you can kind of look at this either in this functional data setting where you observe many trajectories, or maybe in time series where you observe one long trajectory. But for us, we wanted to study the theoretical part, and then we added the numerical results that show it somehow you can actually do something. And no references. I always try to insult everyone equally because otherwise you would miss. So just thanks.
Thank you very much for your talk, Lauri. It was very fun and interesting. Are there any questions?
Yes.
Go ahead, Pablo.
Hello. First of all, thank you very much. It was a great talk. A few questions, short questions. In the general setting of the noise, do you admit a Brownian term, maybe fractional, but also jump diffusion process? I mean, three coefficient functions.
So what we have considered only is kind of this Hölder continuous case. So
Yes.
kind of excluding the jumps. There are basically some results actually doing something similar, but without the Hölder continuous part. So only having the jump terms there.
Mm-hmm.
I would say kind of that, okay, you start with the Brownian case, right? One
Yes.
option is to keep the continuity, but destroying the independence of the increments.
Yeah.
Or another option is to add jumps, but keeping the independence, like changing Brownian motion to Levy. And
Yes.
I don't know anything which would have kind of the both. It's somehow interesting topic, maybe for future, but we only consider kind of the continuous case. And I know few results on the existence and uniqueness of solutions, but kind of then to do what we did here, it's kind of, I would guess it might be doable, but it will be a mess if you look at the technicalities, because kind of then you have to deal with three parts, right?
Yeah.
But once you add the jumps, then your solutions have jumps, and I'm only considering the kind of the fractional Sobolev part we dealt here. And already there, jumps might kind of cause you problems, and you have to deal also on those norms, the jumps, which causes a mess. And then the jump part separately by taking into account this memory part and non-Markovianity of the solution.
Yeah, I see.
So yeah, might be doable.
I see the complication. Yeah, I see.
Yeah, worth the publication, I would say. Not done. And my intuition says that doable, but it's a mess.
I see. So to summarize, you're basically feeding neural networks with a Sobolev norm, right? Discovering the
Yes.
F and G's. Okay. That's fantastic. That's a great idea.
Yes.
How can we get the recording and the slides, if possible?
The recording will be in our YouTube channel. The slides, I don't know if Lauri can share it with us.
I can send it.
Yeah. you can ask the organizers, replying to the email in the invitation.
Sure. Thank you so much.
Welcome.
And maybe I should actually mention that we hope the paper will be in archive in like a couple of weeks.
That'll be great. Thank you. Thank you, Lauri, for your time. Great talk.
Thank you.
Are there more questions?
Yeah, if there are no more questions, I would like to ask if you can fit F and G to be multivariate for several correlated assets.
Sorry? F and
Can F and G be multivariate?
yes,
Vector.
so this is kind of, yeah, a priori, kind of you can, as I also, yeah, my slides are still visible. So I'm super lazy, so I just use this notation, but kind of a priori, everything is multidimensional.
So sigma would be a matrix.
Yeah, sigma would be a matrix, and then you multiply with the noise vector, and
Yeah.
you can understand this, but yeah. Let's use the short notation.
Yes.
Yeah.
Fantastic.
But a priori, like in the simulated examples, we also had one bivariate case.
Right. Thank you. That's a great topic.
Anyone else? If not, I have a couple small questions. At some point, you said, Lauri, that you can combine this because I had the impression that it works very well for the drift, but not so much for the diffusion. But in that case, you just can like estimate the diffusion first with quadratic variation and then use like this technique for the drift. I understood well?
Yeah, for example, I mean, the theoretical part is that we don't kind of say what to use, just kind of quantify the error, right? And then it's user specific. So you choose what method to use, and like in particular in these our cases where everything is actually not time dependent. Let's say I would have a long enough series. In univariate case, you don't need networks. And if the network does for drift well, precisely, then maybe the quadratic variation works for diffusion quite nicely, right? In particular, if h is smaller, because you get better results for the diffusion with larger h as well. But for smaller, use maybe quadratic variation. The drift does not have an effect because it's smooth, right? And yes, and then you can maybe try to drift with other ways. This is what I would try, but
Okay, before giving...
I mean, the numerical part was not the main issue of the paper, so...
No, of course.
I just wanted to show you these very nice colors.
Yes. And Lauri, before giving Pablo the word again, just a small question. Just you said at some point we dropped the time dependency, and I got a little lost. It's just maybe you can develop a little bit on that.
So yeah, basically here in the main result we allow for time dependence. What I simply meant is that basically, if you think about in practice and you have one trajectory, you have no chance to find from one trajectory anything if this has time dependence, right? And this is kind of obvious because you don't know how it evolves in time. So you have one single number on that time instance, right? And then it can be anything. This is what I tried to explain, that kind of you need to drop that if you want to get from along one trajectory. But if you have many trajectories, then you have kind of for each time slice, you have still many numbers and you can try to do something. This is what I meant.
Perfect. Thank you. It was very clear answer. Pablo, go ahead. You have the floor.
Thank you. Thank you. I would like to know what's the relationship between the alpha and the Hurst exponent, because how would you choose the Sobolev norm to fit before knowing this?
So basically, so here it is.
Yeah.
A priori, if you know the H, this is the range you have to choose to alpha. And in practice, what happens is that kind of the lower value of alpha somehow measures more precisely the fluctuations. If you look at kind of the semi-norm part, so you have the Hölder continuity of F, let's say, and the integral takes the +1 away. And what your solution actually is, it lives in this space, and you can show that it's even actually 1 minus alpha, sorry, even 1 minus H Hölder continuous. Yes, no, sorry, 1 minus alpha. Basically, but okay. It's Hölder continuous up to 1 minus H, right? And now if you choose alpha precisely close to that, then you're essentially measuring the Hölder constant or Hölder fluctuations. So in practice, kind of what also was visible, what I forgot to mention, is that if you choose alpha large in your fitting, it gives worse results because you want to kind of measure the Hölder fluctuations.
Yes.
And it's precisely this lower bound. Was this clear enough?
Yeah, it helps a lot. It helps a lot. I mean, alpha depends on H, and you use the alpha to estimate the H in bounding the norm. So
Yeah, but okay, or yeah, alpha kind of depends. So there's a range of alpha that you can choose.
okay.
And a priori, in practice, I can choose whatever alpha I want. But the
I
solution
see.
would give you infinity norm, right? If I
Yes.
choose the wrong one.
Yes.
And most likely your numerical stuff would not give good results with that choice.
I see.
But
Okay.
kind of theoretically, is choose alpha from this range, whatever you want to choose, you have the unique solution in that space.
I see. Perfect. Thank you very much.
Okay. If there aren't any more questions, I would say we thanks again to Lauri for this wonderful talk. Also for staying with us at this hour. For him, it's very late.
Thank you. Yeah, it's 11 p.m.
Thank you very much for the effort, Lauri. It was a real pleasure, and I hope next time could be here with us in three-dimensional.
Definitely. Would love to visit.
Perfect.
Okay. My pleasure.
Okay, well, this
Bye.
finish our session of today.